In this session, let us learn about biasing a diode. Biasing implies giving external DC voltage to a diode so that the diode can be used in building an useful circuit. Biasing also makes the diode current flow unidirectional, which means the current flows in only one direction. And dominated by majority carriers. We will talk about minority carriers little later. Now, there are many diode types. LED or light emitting diode is a type of diode which emits light and is used in lighting applications, including mobile phones. If this is a mobile phone, you might have seen a small LED which is blinking and it changes colors based on the notification. So, the charging or message received indicator lights, which are red, blue, or other colors, are all basically LEDs which show the notification. In the previous video, we learned that a PN diode is formed by chemically joining P and N semiconductors. Now, let us see what happens when we connect a DC voltage to these PN diodes. This is our PN diode. And these are the metallic contacts, and this is the wire, this is my battery, this is the positive terminal of the battery, this is negative terminal of the battery. And these are metallic contacts. And this is a wire. Note that we cannot directly connect the wires to P and N semiconductors, and hence we need a metallic contact. It should be noted that the metallic contact should not hinder the PN junction functionality in any manner. That is, the diode's basic properties should not change due to addition of metallic contact. But since it is a metal contact, it will have some resistance like metals, and hence it is called as an ohmic contact. So, why is this called as an ohmic contact? This is because resistance is measured in ohms. This resistance slightly reduces the amount of current flow, but the diode designers ensure that it is very minimal. Now let us come to biasing of the diode. There are two ways to bias a diode. One is forward bias and other one is the reverse bias. This picture shows the forward bias. When positive terminal of battery is connected to P side of semiconductor and negative terminal is connected to N side of semiconductor, then it is called as forward bias. Here, positive terminal of the battery is connected to P side while negative terminal of the battery is connected to the N side. When the connections are opposite, it is called as reverse bias. Biased diodes are used in many complex applications, and like every other electronic device, we do denote this diode with a symbol. So for a diode, this is the symbol. This is the positive terminal and this is the negative terminal. The positive terminal is called as an anode and negative terminal is called as a cathode. So in diode circuits, you will always see this symbol and you should be able to recognize it as a diode. The metallic contacts connected to P or N sides denote the connections of diode with external circuits. So these anode and cathode terminals are called as electrodes. Now let us see what happens when a diode is connected in a forward biased mode. This is the P side, this is the N side, and this is our barrier potential. So these are all positive charges, these are all negative charges, and these are ions. And this forms a barrier potential. Now these are our metallic contacts. It is connected to a wire to a battery. This is the positive terminal of the battery, this is negative terminal of the battery. So the conventional current flows in this direction, while the electron current flows in this direction. Let us see what are these two currents. This is conventional current. This is electron current. Remember from previous session that the diode without any connection is in a steady state with the diffusion and drift effects leading to charge movement and the formation of this barrier potential. Now in forward bias, the majority carriers or the holes, these are the holes in P junction, get repelled as the positive terminal of the battery is connected to P material. The positive charge from the battery pushes these holes towards the junction, while the negative charge from the battery pushes electrons in N material towards the junction because of the negative potential here. The other way to look at this is that the positive terminal of battery pulls the electrons like this. This positive terminal pulls the electrons towards this side, and on the N side the negative terminal pulls the holes towards this side. But they don't cross. Why? There is a barrier potential to overcome which is opposite compared to the battery voltage. So if you see, the battery voltage is plus and minus, but the barrier potential is opposite. Once the barrier potential is overcome, which is about 0.6 volts for silicon, the holes and electrons cross into opposite region and current or charge flow continues till the battery is supplying energy. Now, this is the conventional current flow or the well-known way of representing current, while the actual current or the electron current is in the opposite direction. Consider a simple circuit. Let's say this is the battery and I have a simple bulb here. And let's say make a connection like this to the bulb. Now this is the positive terminal of the battery, this is negative terminal, and this is my bulb. Now the conventional current, it's in this direction. While the electron current, it's in the opposite direction. This is the electron current. This is the conventional current. Current in P region is due to holes and hence it is called as the hole current, while in the N region it is due to electrons and hence it is called as the electron current. And remember, both these currents are due to majority charge carriers. Since the current is due to forward biasing of diode, the current is called as forward current. Now let us see what happens when a diode is connected in reverse bias. It would be the opposite effect. This is the diode, this is my P region, this is my N region. These are the ions sorry, these are the positive charges and this is the negative charge, and these are the ions. And this is my battery potential. This is my barrier potential. Let's say for silicon it's 0.6 volts. These are my metallic contacts. Note the difference is the battery is connected in an opposite fashion compared to forward bias. This is the positive, this is the negative. Now the minority carriers or the electrons in P junction get repelled as the negative terminal of battery is connected to P material. The negative charge from the battery pushes electrons towards the junction, while positive charge from the battery pushes holes in N material towards the junction. So clearly, if you see, this is a negative terminal and these are holes which are positive, so it is going to pull towards this side, while the negative charges here get pulled towards this side. So what does this mean? This means that the barrier becomes wide for any majority charge carrier to cross over, while minority carriers can cross over due to strong pull from the battery. The minority carriers here are negative charges and they get pushed towards this side, while the minority carriers here are positive charges. They get pushed towards P region because of the positive terminal, which means that the minority charges can easily cross the barrier while the majority charge carriers cannot cross the barrier easily. Thus, in reverse bias, only minority charge carriers cross to create current called as reverse current. As minority charge carriers are small in number, the reverse current is very small compared to forward current, which is due to majority carriers. For a given temperature, and with reverse voltage, this is the reverse voltage. If it is less than the breakdown voltage limit, the reverse current is almost constant, implies a reverse voltage is increased, but if it is less than the breakdown voltage, then the current does not increase much. Thus, we can call the diode is saturated, and hence this current is called as saturation current. Don't worry if you did not understand about saturation current. We will see what is a breakdown region or a breakdown voltage and also little more about saturation current in the upcoming session.